Now let's talk about some of the basic reactions and preparations that we can. Now let's talk about some of the ways to make carboxylic acids that we've covered in prior chapters, and also some of the simple reactions of carboxylic acids that we've seen before, as well as ones that are closely related. So first, from Chem 2131, we might remember the oxidation of alcohols. Here, if we have a primary alcohol, we can oxidize it to a carboxylic acid by doing the Jones oxidation. This is treating it with a chromium-6 salt in the presence of a strong acid in aqueous solution. Similarly, we may have seen this reaction before in Chem 2131. This is not always covered in class, but it's one that I personally like a lot. This is what's known as a carbonation reaction, and it starts with an organometallic reagent. If we start with an organometallic reagent, either an organolithium or Grignard reagent, we can treat it with solid carbon dioxide, aka dry ice, followed by an acidic solution workup to get a carboxylic acid. This reaction works because, much like ketones and aldehydes, the carbonyl carbon of CO2 is actually quite electrophilic. There are also some newer reactions that we've used to prepare carboxylic acids. Specifically, one of the first ones we encountered this semester was the benzylic side chain oxidation in the aromatic chapter. Here, we can take an aromatic ring as long as we have a carbon with a hydrogen in the benzylic position. Strong oxidizing agents like potassium permanganate or potassium dichromate will oxidize that to a carboxylic acid. Remember that we did not cover the mechanism of this process, and we are not going to. It's fairly complicated and well outside the scope of our course. One completely new reaction that's covered in this chapter is the hydrolysis of nitriles. So this is often useful if we want to prepare a carboxylic acid from an alkyl halide, especially primary or secondary, where an SN2 reaction is possible. If we take haloalkane like this and treat it with potassium cyanide and DMSO, we can do an SN2 reaction to get a nitrile. Nitriles can be hydrolyzed in a solution of acidic water while heated to produce carboxylic acids. Shifting gears a little bit, let's talk about some of the reactions of carboxylic acids that we've seen before, specifically the reductions. Back in Chem 2131, we covered the lithium aluminum hydride reduction of carboxylic acids, which produces primary alcohols. One thing that we did not cover in Chem 2131 is what the mechanism of this reaction is, so let's talk a little bit about that now. If we combine a carboxylic acid and lithium aluminum hydride, the first thing to remember is that lithium aluminum hydride is a fairly strong base and reacts with protic solvents. That means that the first thing that will happen with this carboxylic acid is a proton transfer to give a carboxylate ion, AlH3 or alumane, and hydrogen gas. Next, the nucleophilic hydrogen of AlH3 can add to the carbonyl carbon, while at the same time the carbonyl oxygen will form a bond to the aluminum atom, which is a strong Lewis acid. This produces this aluminum-containing intermediate. Now, as we've seen before, the negative charge of an oxygen atom like this can easily kick out stabilized leaving groups. So this oxygen will regenerate the aldehyde, while this will kick out the aluminum salt. This produces an aldehyde, and aldehydes, as we saw in Chem 2131, are very easily reduced under these conditions. So if you want to know more about that, go back to the alcohol chapter in Chem 2131 and look at the hydride reduction of ketones and aldehydes. There's also a familiar reducing reagent that we can use in this new circumstance, which is borane, or BH3. If we take a compound like this that contains both a carboxylic acid as well as some other carbonyl derivatives like ketones or aldehydes and treat it with a solution of BH3 and THF, we're going to selectively reduce the carboxylic acid in the presence of other carbonyl groups. So in this case, we will get a primary alcohol from the carboxylic acid without reducing the carbonyl group of the ketone as well. This is useful because it means that we do not have to use a protection-deprotection strategy in the presence of ketones or aldehydes. So let's try this. Let's practice a little bit. First, let's take a look at a synthesis problem. This compound here is called phthalic acid. Phthalic acid and its derivatives are quite useful in a lot of plastics applications. So what I'd like you to do for me here is propose a synthesis of phthalic acid starting from orthobromotoluene. Pause the video, take a few minutes to work through this, and come back when you're done. One thing to be careful about in this synthesis is the order of addition, the order in which you do the steps. If we're looking at this, our retrosynthetic analysis might include the methyl group being oxidized to the carboxylic acid and the aryl halide being used for a carbonation reaction to produce the other carboxylic acid. But we have to do these in the right order. We can't oxidize the methyl group first because production of the Grignard reagent after that step would result in an intramolecular proton transfer. So the way that will work for this is initially converting the aryl halide into a Grignard reagent by treatment with magnesium and ether. Note that there's no acidic protons in this compound, so this reagent would work as we've suggested. Next, we can carbonate this Grignard reagent to produce one carboxylic acid. And finally, we can take that methyl group and oxidize it to a second carboxylic acid. As the initial carboxylic acid has no benzylic hydrogens, it is immune to further oxidation, and therefore this reaction will proceed exactly as we've proposed. Let's do a little reagent practice also. Let's take this compound here, which contains both a ketone and a carboxylic acid, and show the products, first of reduction with BH3 and THF, and second after the reduction with lithium aluminum hydride, followed by workup with water. Take a few minutes, work through these reactions. Be careful to draw any intermediates for the two-step reactions, then come back and check your work. The reaction with borane should have been fairly straightforward. As we saw on the previous slide, borane reduction is selective for the carboxylic acid over the ketone. So we would result in this compound here, which has a ketone and a primary alcohol. For the lithium aluminum hydride reduction, however, our analysis is much more complicated. So the first thing that would likely happen here is that the lithium aluminum hydride would pick up a proton from the carboxylic acid. It is quite basic. The second thing that would happen is that ketones are reduced much, much faster than carboxylates, so it's the ketone that's actually going to be reduced by our reagent here. Finally, in the workup step, we would be able to protonate the alcohol, which would be more basic than hydroxide. We will not be able to reprotonate the carboxylate, which will be significantly less basic than hydroxide. So our final product in this reaction is actually this carboxylate salt. Note that reduction has only occurred from the ketone to the secondary alcohol. That concludes the topics for this video. Next, we're going to talk about the primary mechanism of reaction with carboxylates and their derivatives, nucleophilic acyl substitution.